Hi everyone, Joe here, bringing you a video on how to do force diagrams. Force diagrams are really important in the forces unit because they allow us to understand all the different directions that a forces might be acting in a particular situation, in a particular problem. So I'm going to bring you 10 rules in total, 5 rules that are kind of the basics, the building blocks, and then 5 rules to help us tackle even more advanced problems. So to dive right into it, we're going to start with a pretty simple example of a book which is at rest on a table. Because it's at rest, we know it's maintaining a constant velocity of 0 meters per second. Because it's maintaining a constant velocity, by Newton's first law, we know that the forces must be balanced. So let's draw a force diagram where the forces on the book are balanced. The first thing that we're going to do is we're going to need to show exactly what we're drawing the forces on. So for this problem, it's pretty easy. It's pretty clear. We know that we're drawing the forces on the book. But when we get into more advanced problems, it might become a little bit more complicated. We might be combining different objects. So it's going to be really important that we show our system boundaries starting from the very beginning. So I'm going to draw a dashed line to show what we're drawing the forces on. And we're drawing all the forces on the book. So I'm going to put a dashed line around the book. Rule number 2 is that you don't want to draw directly on whatever image you're provided because then it can get really cluttered, really complicated. So over off to the side, as you can see I've done here, we're going to represent the book either with a dot or a box. Either works, and I'll show you both in this presentation so you can kind of see both of the different ways to do it. So over on the left, I've drawn a box and I've labeled it book. Rule number 3 is that we're going to show all the forces starting at the object and emanating outwards. And this is just a convention. Even if I were to come over and I would have pushed down on top of the box, we would not use that red arrow. And that's just a convention because scientists expect all force diagrams to look the same way. And we don't want to be looking all around for all the forces acting in the downward direction. So scientists just agreed if the force is acting down, it goes below the box pointing down. It just makes it easy to see where all the forces are acting. And the other thing I'll mention here is that in a force diagram, you only show non-negligible forces. So if a force is really small and we can ignore it, you don't put it in the force diagram. This is going to come up with problems where there's just a tiny bit of air resistance, but it's so small it can be ignored. So just make sure that in your force diagram, you have no negligible forces. Rule number 4 is that the arrow length is actually really important. The arrow length shows magnitude. So you'll see here that I've drawn my 2 arrows. I've tried my very best to have them be the same length, but just to make it really clear that they're the same length, I've used equality marks as well. I know they're the same length because Newton's first law tells me that the forces must be balanced. So all the force up has to be balanced out with all the force down. So the arrow length does show magnitude. A longer arrow shows more force. And we want to try to be as accurate with that as possible. So if you're trying to show the forces to be unbalanced, go ahead and exaggerate it. Make your force extra long to show that the forces are unbalanced in a particular direction. And rule number 5 is kind of the last rule in our basics building block set, is that then the last thing we need to do is label our forces. We need to label it with its name and something called a by-on notation. So for example, I've labeled force gravity, which is by the Earth on the book, because the center of the planet is pulling down on all of the things on the surface of the planet. So it's pulling down, which is why it's by Earth on book. And the force normal tells us that the table, by table on book, the table is pushing back up on the book to counteract the force of gravity and make sure that the forces stay balanced. It's really important that we include the by-on notation, especially at the beginning, because it helps us keep track of what is doing the force and what is receiving the force. So since this is a force diagram for all the forces on the book, our by-on notation should always be by something on book. If you ever have by book on something else, that's for a different force diagram, because these are all the forces on the book, not for the forces by the book. So those are kind of the 5 basic building blocks, which can get you started on doing some force diagrams. But I also didn't want to just let you have just the basic rules. I wanted to get into the advanced stuff as well. So the next 5 are going to be for when we start to get into more complicated, maybe even more interesting scenarios. So rule number 6 is that you can't have more than one force acting in any direction. So in this example, you can see that we have 2 forces pulling to the left and 1 force pulling to the right. But let's imagine that the forces on the cart are still balanced. So we're going to need to have an equal amount of force pulling to the left as we have force pulling to the right. So what that force diagram might look like is we might have two forces pulling to the left and one force pulling to the right. But you'll notice that if I add up the little arrows for force tension 1 and force tension 2, the two arrows should add up to be the length of force tension 3. So it might be a little bit hard to see here, but the way that we're going to normally do problems like this is I'll give it to you on a grid. So you can have force tension 1 go over 1 square on the grid, because remember the length represents the magnitude. Then if force tension 2 goes over 2 squares, we have a total of 3 squares moving to the left, and we can balance that out by having 3 squares moving to the right for force tension 3. The other thing I want to point out in this scenario is that you'll notice that I have an equality mark on force normal going up and force gravity going down, but I don't have any equality marks in the horizontal direction. And that's because 1 does not equal 2 does not equal 3. Even though 1 plus 2 gives us 3 to the left, we have 3 to the left and 3 to the right. It wouldn't be right to show equality marks on any of those horizontal forces. Rule number 7 is that normal force does not always equal weight. Weight is a synonym for force gravity. And in the previous examples, you can see that we've had force normal being equal to force gravity, which is true a lot of the time, but it's not always true. And I don't want you to get the wrong idea that they were always true. For example, if you were to stand on a scale, the scale would tell you the force normal. And if you were to stand on the scale correctly, then the force normal would be equal to force gravity. But if your friend, for example, came over and pushed down on your shoulders, the reading on the scale would shoot up. That's not because you gained weight. It's not because you gained force gravity. It's because now there are two forces in the down direction, force gravity and the force by your friend down on your shoulders, an applied force, which causes the reading on the scale to go up. The normal force goes up. So two important things to note here is that scales read normal force because the only thing the scale knows is how hard it's having to push up on you. So if your friend is pushing down your shoulders, the scale has to work extra hard. So scales read normal force, not force gravity. It's just 99% of the time when you use a scale, if you use it correctly, the normal force, the reading on the scale is equal to your weight, is equal to your force gravity. And the other thing to write down is that weight and force gravity are synonyms, whereas weight and mass are not synonyms. But weight and force gravity are synonyms because weight is a force and mass is a different thing that is connected to force. Rule number 8 is that forces are not always entirely horizontal or vertical. So for example, in this problem, you'll notice that there's a force to the left, there's gravity pulling straight down, and then there's also going to be a force that is kind of up and to the right. The force that's up and to the right has a part of that force that is up and a part of that force that's to the right. But let's say that the forces are still balanced, and we would know that because it's maintaining a constant velocity. Then the forces have to be balanced in the horizontal direction, and they also have to be balanced in the vertical direction. So what this would look like is in your force diagram, I've drawn two squares of force going to the left, and you'll notice in my force tension on the right, it goes over 1, 2 squares to show it's balanced in the horizontal direction. I have force gravity as 1, 2, 3, 4 squares down, and you'll notice for force tension, the one on the right, I had to go up 1, 2, 3, 4 squares. So this is still showing an object which has balanced forces, even though one of them is at a diagonal. The diagonal has a horizontal component of 2 squares to the right and a vertical component of 4 squares up. And that's how you can show forces still being balanced, even if one of them is at an angle. Rule number 9, which is important, is that we actually look at the horizontal direction differently from the vertical direction. So in the example of a rocket ship, which is accelerating upwards, we want to have an unbalanced force in the vertical direction, but in the horizontal direction, we want to make sure the forces are balanced. Otherwise, the rocket ship may go left or right, which we would not want. So what that would look like is here I have the forces in the vertical direction. You can see that they're balanced, but in the horizontal direction, you can see that they are, in the vertical direction, the forces are unbalanced, whereas in the horizontal direction, the forces are balanced. This is good because we want the rocket ship to accelerate upwards while maintaining a constant velocity in the horizontal direction. So just important thing to know is we can look at vertical and horizontal separately. Actually, I said we can look at them separately. What I should have said is we must look at them separately. Vertical and horizontal operate independently. So we can look at them as such. And the last rule is that certain forces always act in particular directions. And we can depend on those directions to kind of build our force diagrams up around it. So the classic example is a box that's sitting stationary on a ramp. If it's stationary on a ramp, the forces still have to be balanced, but it kind of becomes a little bit more interesting when things get to be at an angle. So the first force that we can always rely on is gravity pulling straight down. That's going to be true basically in every force diagram that we're going to see in this class anyway. The next force that we can rely on is the force friction, which is always going to be in the opposite direction of motion. So it's kind of confusing because what's the direction of motion for an object that's stationary? I like to think about what's maybe not motion, but what I call desired motion, which is if friction were to disappear, which direction would the object slide? So without friction, the object would slide down and to the left. Therefore, friction must be up and to the right. Because friction is caused by the two surfaces rubbing together, that up and to the right is also going to be parallel to the surface. And last but not least, normal force is caused by the surface pushing up on the block. So in this circumstance, actually in all circumstances, normal force is perpendicular to the surface. So while friction force is parallel to the surface, normal force is perpendicular to the surface. So you'll notice those two forces are going to be at a right angle. And actually, if we know the slope of the surface, we can figure out the slope of the normal force by taking the opposite reciprocal of the slope of the surface. So that's going to give us the perpendicular or right angle so that we can make sure it's perfectly a right angle. The normal force is perpendicular to the surface because it's the surface that's doing the pushing. I know that was a lot. That was all 10 rules kind of all at once, but I wanted to give you all the information so that you could start to practice force diagrams, start to wrap your head around it. We're going to be discussing this in our next class. So please do your best try at the practice problems. Write down any questions that you may have, and I'm looking forward to discussing with them next time I see you.